Hello, today we're going to look at how we're using limits to determine continuity of a function and apply the intermediate value theorem. We'll also use limits to describe end behavior. Now, limits is a new word, something you haven't seen before. It kind of goes off of domain and range, but it's really talking about where a graph is going as it approaches maybe the end of the visual graph, which direction it's heading. We'll learn about that as we go. There's a lot of new vocabulary terms. Again, there's that word limit. Continuous means no breaks, so function will not have any breaks. Discontinuous obviously means there is some type of break inside the graph. Infinite discontinuity is when there's an asymptote that is the break, so I'll call it an asymptotic break. A jump is where the graph jumps from one place to another. Removable is when one little piece has been removed, like one, I'll do here in quotes, a one dot has been removed. We'll see what this looks like in a little while. And non-removable discontinuity is when there is a dot, but it's been placed somewhere else. In behaviors, what's happening on the graph is you look at the far left and far right. Left-sided would be on the left side of a break. The right side is on the right side of a break. So we'll see those as we go. A limit. Here's what the actual definition of a limit is. It says the value of x approaches a unique value L, such as x approaches c from each side. The limit of f of x approaches c is L. Now that's really, really confusing. Here's how it looks as a symbol. And the best way to think of a limit is to read this a certain way. And so whenever you see limit, here's what I want you to think of. I want you to think of what happens to y. Now remember, f of x is the same thing as y. So this is what happens to y as x approaches some value. I'll just do a blank here so you know. That will plug in something else there. So that's how you read this. What happens to y as x approaches some value. So this is what happens to y as x approaches, here in this case, c. Now I'll show you a problem, and you'll get to see how we use this in actual math. Again, the types of discontinuity, we talked about 3. Infinite, this means there's a break of an asymptote in here. So if I insert in an asymptote here for you, it would kind of show you, well, that would be an infinite discontinuity because it's being broken by a line that's infinite, extends both ways. This is jump. You see how the graph jumps from down here to up here. And removable, again, is when one little piece has been removed. You see how that's like one little dot has been removed? Non-removable would simply be if that dot was picked up and moved, say, down here. That would then become non-removable, just like that. Okay? Continuity test. So the easiest way is just to look at a graph. So this is talking about different ways using limits for continuity. I'm not going to get into that as much from here, but I'll let you see the algebra of it later. All right, so first, it says identify a point of continuity. It says determine whether f of x equals 1 over 2x plus 1 is continuous at x equals 1/2. Justify using the continuity test. All right, first, if we look at the graph, we'd be able to tell really quickly if this is continuous or not. Here's the graph. Now, on this graph, you can see that the graph itself, the whole function, let me rephrase, the function is discontinuity. The function has infinite discontinuity. However, I'll finish writing here. And that's infinite discontinuity because of this line that can break it right here. But at the spot x equals 1/2, it's actually continuous because this is the spot we want to look at. At this spot, is it continuous? Determine that using algebra. What you do is you plug in that 1/2 value for x. So the function at 1/2 is equal to, let me pull up the equation again, there it is, 1 over 2 times 1/2 plus 1. If I went to simplify this, I'd find out that this is the same thing as 1 over 2 times 1/2 is 1, 1 plus 1. And so we get a value of 1/2. So we see that here, if the x is 1/2, we should have the coordinate point 1/2, comma, 1/2. We look at the picture, and that's exactly what it says. So then to determine if it's continuous, you just have to make sure the left side of the graph, the left end behavior, is approaching the same point as the right side. Are these, both of these I just drawn in these arrows, are these both approaching the same point? Yes, they are. Because of that, it is continuous at x equals 1/2.